Hello again, AP Stats. This is Mrs. Harding. Today I'm going to walk you through activity 1.3a. What we've discussed in previous lessons was on distributions of quantitative data and how to describe those distributions. In the descriptions, we talked about shape, center, and variability. We're going to dig a little deeper in this activity. You can see the learning targets on the screen. It says calculates measures of center. So we're going to talk about mean and median. Both of those concepts I'm confident you already know how to determine, but we're going to look at how it's affected by the shape of the graph. We're going to calculate and interpret measures of variability, range, standard deviation later on, IQR today. Explain how outliers and skewness can affect both of the center and the variability. And we're going to talk about the specific rule for determining an outlier. Before, when we mentioned outliers in a distribution, we said there were likely outliers just based on the visual that you see on the graph. Today we're going to talk about a specific measurement to determine if something is actually an outlier. So the data that we're going to start with we've used before. The percentage of the population by state of residents that are 65 or older. And let's move down here to the actual relative frequency histogram. And you can see here the shape of this histogram. I think that we've looked at this before. The shape of this histogram is symmetric. So let's think about where we might place that measure of center. There's an arrow that you can see on the screen. That might be a good place to put the measure of center. But let's be specific here with mean and median. How exactly are we locating mean and median in the picture? Well, the mean is the average. You know how to calculate that. But in the picture, we're thinking about the balancing point of the graph. If you had to balance that entire histogram at one point, where would that point be? And that would be your mean. As opposed to the median. When you figure out a median, you're ordering your numbers and you're finding what's in the middle. You're dividing your data set into two equal parts. So when you look at a histogram, you're dividing your histogram into two equal areas so that to the left and to the right of the median you have equal areas. In this particular case, you probably guessed them to be very close to each other. And that is actually the case. The mean is 12.71 and the median is 12.75. Let's take a look at a different graph and try and do the same process. So in here, this is a graph of the relative frequency of the length of words in Shakespeare's plays. How would you describe the shape of this graph? Hopefully you said that this graph was skewed to the right. So how is that going to affect your mean and your median? Well, take a look at these two lines that are drawn in there. The median divides the graph into two equal areas. The mean is the balancing point, and this time, if you imagine balancing it, you need to be a little bit more to the right to balance it because you have these larger values out at 10, 11, 12, and so it's sort of weighing down the right end of the graph. On a graph that is skewed right, your mean is going to be slightly higher than your median because of these values that are out at the larger amounts. All right, let's take a look at a third graph. We're going to actually play with this one a little bit. This one is in a Fathom file that I can move around for you. So for just a moment, what is the shape of this graph? Hopefully you said skewed left. And there on the screen you can see what the actual mean and the median are. The mean is 1.03. The median is 1.08. And you can see them marked on the graph as well. Here is the median, here is the mean. And you can see that the mean is slightly less than the median this time. If we needed equal areas, we would draw a line here. If we needed to balance, we would draw the line there because of these smaller values down here that sort of pull the mean in that direction. They pull the mean to the smaller numbers. So in this case, the mean is less than the median. But let's take a look at that actual file. And I'm going to play around with it a little bit with you. In here, I can slide this bar around and it will change the shape of the graph. And what you can take a look at is that when I have a graph that seems a little bit more symmetric, let me get one there for you, the mean and the median tend to be about the same, 0.749, 0.75. If I have a graph that is a little more skewed to the left. Get one out here for you. You can see here that the mean is actually, oops, these are skewed right, my apologies. When it's skewed right, the mean is 0.26, the median is 0.25. If I come up with something that's a little bit more skewed to the left, like the original, you can see in here then that the mean and the median change according to what the shape of the graph looks like. So then we're back to where we started here, skewed left, the mean is 1.04, the median is 1.08. So let's actually write that down specifically so that you can keep them straight. On the next page, what is the rule then that we follow? When a distribution is symmetric, the mean and the median are relatively the same. When a distribution is skewed left, the mean gets pulled in the direction of the skew, and therefore the mean is less than the median. For a distribution that's skewed right, again, the skew pulls the mean in that direction. So when it's skewed right, the mean is actually greater than the median. And so looking at this new distribution, this has the highway miles per gallon for a set of cars. It says 106 automobiles. Think about what shape you would say that is. Is it symmetric? Is it skewed right? Is it skewed left? And based on this shape, how would you say that the mean and the median relate to each other? Well, you should have looked at that as slightly skewed to the right, which would pull the mean towards the larger values. The mean would be larger than the median, and then the actual numbers are given there at the bottom. The actual mean is 28.7, actual median is 28.5, so you can see that the mean is a little bit larger. But let's take a look at this next page. There are several different distributions here of the categorical variable type of car. So now it's broken down, the highway miles per gallon, into type of car. And you're looking at a lot of different distributions. So what I would like you to do now is pause the video, and I want you to answer the questions at the bottom of this page. Okay, the distribution with the greatest mean, the largest mean, was the small size cars. The smallest mean is the luxury or the upscale cars. Does this make sense? I would think so. On the next page, it asks you, what do you expect to be true about the relation between mean highway miles per gallon and median highway miles per gallon for sports cars? So let's take a look at this distribution here for the sports cars. In here, if you were to talk about the shape of this, you've got the bulk of the data here, but then there's this big outlier up there. So what would we expect to happen with that skew to the right? We would expect the mean to be larger than the median. And in fact, the actual mean is 28.2, the actual median is 28.0. So when should you choose the mean and when should you choose the median? Because skewness has such a strong impact on mean, anytime you have a graph that is skewed to the left, skewed to the right, or there are outliers, you should use the measure of the median to describe the center of the graph. The median is said to be resistant to outliers and skewness, as opposed to the mean, which is very much impacted by a skew and by outliers. So if you have a graph that is skewed or has outliers, you want to report the mean as the center of the graph. If you have a graph that is symmetric and there are no outliers, then you can go ahead and report the mean as the center of the graph. Outliers are a key player here. Sometimes you can have a graph that's pretty much symmetric with the exception of one outlier. In that case, you're still going to use the median as the measure of center because of that outlier. Anytime you see an outlier, you want to use median as your measure of center. All right, so let's take a look at a couple of other characteristics here. And we're going to talk about the IQR. It says, let's return to the car data. The table below shows data for just families of cars, for family cars. Sorry, apparently my reading is a little rough today. Well, when you go through and you find the median or mean, when you find the mean, you guys know in general, you're adding it all together and then you're dividing by how many there are. But I want to talk just really quickly about the formula and some notation. So you can see there's an actual formula written down here. First of all, X bar is the representation for mean. So this is calculating X bar. You know that this means the sum. X subscript I represents all the individual data. So this is the individual X values. And as we've sort of already seen in some of our sampling, N is the sample size. So you want to get comfortable with this notation. And it says this is how it will be presented to you on the formula sheet. Very soon we'll start showing you the formula sheet, start talking about different things that are on it. But you need to know what the different formulas are going to look like on the formula sheet. But if we wanted to do some other calculations with this, you can enter all this into your calculator. We can actually find the median of this a little bit more quickly with your calculator. So I'm going to just have you pause for a second. And I want you to enter these numbers in the table into your calculator. Okay, once you have your list in your calculator, you can actually have your calculator order the list. I'm going to show you a quick command in here. If you hit the Stat button, and do you see how number 2 says sort A, that's sort ascending and then sort descending? So I can select number 2. And I can tell it which list to sort. So second one puts an L1 on the screen. When you hit enter, you'll see done. But then if you go to your list, you're going to notice now that the list has been sorted in increasing order. So that's a really quick way to order a list of numbers that are not in order. So let's go back to our data and what we're going to look at in regards to this data. It says locate the middle of the data and label it the median. So the median in this case is going to be at 29. What percentile is Q2? Well, it's in the very middle of the data, so that means 50% of the data is less than 29. Then in the next two steps, we're going to calculate the lower and upper quartiles. So you're going to take the lower half of the data and split it in half. You're going to do that at 28. What quartile is this in? That is in the 25th percentile. 25% of the data is less than 28. And then do the same thing for the upper quartile. Find the middle of the upper half. And you should come up with 30. What percentile is this? It's the 75th percentile. Perhaps you've done all of this before. But we're going to take a look at something called the IQR now. The difference between the upper and lower quartiles is called the interquartile range, or the IQR. The IQR is a measure of variability. So do you remember when I was telling you that the range really doesn't get used that much in the long run? Well, in favor of the range, often we'll be using standard deviation or this, which is called IQR. The IQR for this data is the difference between Q1 and Q3, and the IQR is 2. What portion of the distribution lies within the first and third quartiles? That is 50% of the data lies in that spot. What is the range of the middle 50% called? It's called the IQR. So we'll talk about IQR in all these different ways. The middle 50%, the difference between the upper and the lower quartiles. But this is what we're going to use as a measure of spread. All right. So besides being a measure of variability, the IQR is also used for identifying outliers. So here's where we're going to actually talk about some outliers in this data. The way that you determine an outlier is something that is more than 1.5 times the IQR above the third quartile or below the first quartile. So here's what we're going to figure out. We're going to figure out the upper cutoff. So the Q3 plus 1.5 times the IQR will tell me what the cutoff value is for any upper outliers. So we're looking at 30 plus 1.5 times 2 to get 33. So what that means is in your data set, any number larger than 33 is considered an outlier. On the lower end, I'm going to do Q1 minus 1.5 times IQR. So this is going to be 28 minus 1.5 times 2 to get 25. So any values in your data set that are less than 25 are going to be considered outliers. And in this particular set, there are no outliers. There are no numbers that are larger than 33, and there are no numbers that are less than 25. All right, on the very last page, there is a practice problem for you to check your understanding of these ideas. I'd like you to pause the video and fill out these answers, and then I will go through them with you. Okay, let's take a look at the answers. What you have in there is New Yorker travel times. It's organized into a stem plot. They give you the key there. Each represents a 2-digit number for the number of minutes it takes to get to work. The first question, would you expect the mean travel time to be less than, the same as, or larger than the median? The mean is going to be larger than the median. This is skewed to the right. There are a large amount of commutes out here on the right side, 85 minutes, 65 minutes, 60 minutes. Because this is skewed to the right, we would expect the mean to be larger than the median. And then in fact, in part B, when you figure out those numbers, you will see that that is true. Would the mean or the median be appropriate measure of center for this distribution? Why? Because of the skewness, because of that potential outlier up there at 85, we're going to say that the median is the better descriptor of center because of the skew and because of the outliers, potential outlier. And then in part D, determine if 85 is considered an outlier. Well, we're going to need to figure out, first off, what the first quartile is and what the and the third quartile, so that we can figure out the IQR is 27.5. Using 27.5, we can come up with the lower cutoff number and the upper cutoff number. The lower cutoff number is negative 26.25, so certainly there's no lower outliers. The upper cutoff is 83.75, which does in fact make 87 an outlier. And that brings us to the end of activity 1.3a. As always, if you have questions, please let us know.